Can you hear me? Yeah. I hope I can live up to the, the intro. It's a pleasure to be here. So I've been to SDS a couple of times already, so I'm very happy to be back. Can you hear me? It's okay? It's fine. Excellent. So today I will tell you a bit about what we do in my lab. So I'm the head of this Exascale Info Lab in Fribourg. As Thilo mentioned, also co-founded a company which is doing big data in Switzerland and in Europe. It's called Sagility. You can check it out. First few words about the lab, since you might not know him. We are the neighbors, right, in Fribourg, so not too far away from here, directly connected through the intercity line. I've been in Fribourg for a few years now. And what do we do in Fribourg? That's my group, or part of it. We are doing big data, which is obviously a bit vague, right? So mostly we are building systems, right? So we are more on the applied side of big data, I would say. We are building new infrastructures to manage non-relational data, right? So we are interested in building systems for time series, for social networks, for scientific data, and for text. I will be talking quite a bit about text today. So please visit us if you're in the neighborhood. That's our website. Okay, and today we'll be telling you a bit about this entities story, which we have been studying for the past 4 or 5 years. So let me start with, the famous or infamous V's of big data, right? You all know this colloquial definition of big data. You can have as many V's as you want, but the 3 original V's, which were characterizing big data, were the volume, velocity, and variety, right? So Gartner told us a few years ago that you have a big data problem if you have a lot of data, but perhaps you don't have that much data, but the data is fast, right? Velocity. If you think in terms of disasters, in terms of stock markets, the data is very small actually, but you have to react in milliseconds, in seconds. So that's the second V. And the third V is variety. And my point today is I feel like we've done a tremendous job in terms of tackling volume and velocity, right? If you think in terms of the open source packages, which are now available from Hadoop to Spark to Flink to Storm, we pretty much can use tens of thousands of servers to tackle the volume issue. We have some really nice velocity libraries, right? Spark streaming, Flink, etc. So let's say that we are done with those 2 V's, but we did well in terms of the research community and the industry in building new systems, doing things which are totally impossible 5 years ago, right? Today we'll talk about the third V, variety. Variety is still very tough today. The New York Times says that the data scientists are basically wasting 80% of their time preparing the data, right? And if you've been doing data science, you know that often it is the case, right? Before building the model, you have to search for the data, you have to manually translate the data, glue the data, put this in another store. So basically you spend half of your time or more by cleaning and integrating the data. So why can't we automate this? That's a bit the question today, and I will try to give you some answers. So typically, historically, if you look at computer science, we have this big divide in terms of how to manage information. On the left, you have the kind of Google information retrieval approach, right? Where you search for data using keywords. That's the language, the query language as we call it, right? And then you have an inverted index and a complex crawler search engine which will give you back some answers, like documents containing those keywords. On the other side, that's more the world I'm coming from, you have the structured information management community. So basically the database people, where you have what we call a declarative query language, SQL. So you write those complex SQL queries, it hits a complex box, which is called a database management system, and you get structured answers as the results of this query, right? And historically, those two worlds have been totally separated. So you would use one stack of technology to query documents, and one totally different stack to query tables and structured data. And along those lines, information integration has always been one of the big issues. Actually, some people say, still today, integrating information is what costs most for the companies in terms of expenses for CS problems. So how do you integrate data? I don't know if you try to integrate data automatically. It's really, really difficult. So for unstructured data, obviously, the idea of integrating those documents was to use keywords, right? You have to use the right keywords to be able to retrieve all the relevant documents, or synonym sets, synth sets, query expansion, all kinds of IR artillery kind of strategies to be able to retrieve the documents. For structured data, for relational databases, for 30 years we've been using what we call global schemas, right? Basically you have two databases, two schemas. You build a third schema, which is bigger, which contains everything from the two local schemas, and then, that's basically a view, and you use query writing using views to be able to, using one query, tap into the two databases, right? And you have different ways of doing that, but basically, it's very, very difficult, right? In both cases, you need some sort of a mediation, right? Like synonym sets, a global schema. You need a common ground to be able to integrate the data. And it's very difficult to do that, right? We still don't quite know how to do this for structured data in an automated way. We had, decades of research to do this for documents. And now the big problem that all the medium and especially the big companies are facing today, they want to do both, obviously, right? Today, all the big companies, they have data lakes. You all know about them, where you put all the data such that the analyst can combine the data and build great predictive models out of it. How do we integrate all those pieces of data in the data lake? You have a lot of unstructured data, and you have also a lot of structured data. So that's one of the big problems, I think, today and for the next 5 to 10 years. How are we going to integrate those different pieces of data which are stored in big data lakes before they can be automated and kind of reasoned upon using models, etc. So historically there was no clear way of doing this. What I will be talking about today is how to use entities to have this new mediation layer to be able to integrate all the data in your company or in your institution. So what does that mean? What is an entity, first of all? There is no strict definition, right? It's like a higher level concept. So think in terms of whatever could be a topic for Wikipedia or any Wikipedia-like portal, right? So you could be an entity. I'm an entity online. A session can be an entity, a location, a date, an event, a concept, a software program. All of those are entities. So they're basically, identifiers to refer to a concept or some physical location, person, company, etc. So the idea is not to use tables or keywords, but to use those identifiers of entities and store the information at this kind of higher level layer, right? And then how do you integrate different entities? You simply link them. So it's a very high level, very simplistic way of doing integration, right? Compared to tables, where you build a query, which is basically a view over the different databases schemas, here you simply add an edge between two entities to connect and basically integrate them. So what's the advantage compared to keywords, let's say? Well, we are at what we call the semantic level, right? So if you search in terms of automobile, you will not get answers for cars if you use simple keywords, right? But the entity car represents both, and hopefully, it's described in a detailed manner. It has values, it has properties, it has different kinds of edges going on that you can understand. It both represents automobile and car and voiture in French, so it's kind of, again, a higher level, simple concept. And it's also, it seems, how our brains function, right? We all perceive things, and we have this entity layer, it seems, in our brain to be able to make sense out of the data, right? So today I will try to show you that we can build something similar using knowledge graphs to make sense out of the data you have in your data lake. Compared to relational database management systems, also it has lots of advantages. It's what we call denormalized. You don't need a schema. It can be very sparse, right? And you can pre-compute joins, etc., etc. And it has lots of drawbacks. Think about it. We can talk about it offline. So that's the vision. How do you integrate, from my perspective, different kinds of data, all kinds of data in your data lake? Well, you build this entity layer, we call this a knowledge graph these days, and then you will simply link all your company documents, all your emails, all your web pages, all your tweets, all your tables, all your relational documents. You will link all of those documents to the knowledge graph. And then you can basically build higher level apps by tapping directly into the knowledge graph and getting all kinds of information from the different sources. So we've been doing this for a few years. I will tell you a bit what we did in terms of techniques. I will tell you a bit about applications. But I also want to point out that we are not the only ones doing this, right? Google was a leader in that field with their knowledge graph. Yahoo also was a very early adopter, the BBC, the New York Times, so there are many different organizations today which are using knowledge graphs. The latest one being Amazon, right? They have this big effort which just started to build a knowledge graph for their products. So this is a bit what I will tell you in terms of techniques today. I will tell you a bit how you can integrate text using knowledge graph into your big data platform. Why text? Because it is still the most difficult type of data to integrate, right? We know more or less how to integrate relational, XML, RDF data, more or less manually or semi-manually. Text is still very, very difficult. And that's why I picked it up as a data type, because I think it's still very challenging today. We say that understanding text is AI complete, right? So basically we need a true AI to be able to understand text. And we are not there yet. Perhaps in 15, 20, 30, 40 years, I don't know. So this is the main idea, right? You have text on the left, and we want to have a pipeline which will integrate this text to other kinds of data using a knowledge graph on the right. So we have this pipeline, we call it C pipeline, where basically we try to extract entities from the text automatically. We try to link it to the knowledge base, the knowledge graph. We try to type it using very novel methods. And basically then we try to also co-reference the different labels, the different strings in the text to the same entity. So that's a pipeline we developed in my lab over the past 4 years, I guess. We are still working on it, obviously. And it runs, since we are in a big data lab, it runs on massive clusters using Spark. So let me tell you just a bit about those 4 steps, and then I will tell you a bit about some applications we've developed using this. So the first problem we tackle is called named entity recognition, NER, right? It's basically, you have some text, and you want to understand whether part of the text is an entity or is not an entity, right? Examples. So if I tell you the President of the United States, right? This is clearly an entity. And what does it represent? We don't know yet at this stage, but we can understand as humans that the President of the United States is something which should be linked to something else in the database, in the knowledge graph. If I say in a scientific paper, the figure on the left, right? This might probably not be an entity. It's more like a phrase in a sentence. So this should be basically considered as not an entity. So I will not get into too much detail here. but I will just let you know that we've built this new way of recognizing whether some words represent an entity or not. How do we do that? Well, we take PDFs or any kind of text as input. We do some standard, text normalizations and lemmatization. Then we extract n-grams, and here we use also big data n-grams, like the Google n-grams, so basically tons and tons of statistics about text. And we use all of this using machine learning to then understand whether from a probabilistic perspective, the figure on the left should be treated as an entity or not. Or, for example, another example is structured inverted index, right? This is an entity. You might know inverted index, it's a well-known data structure. Structured inverted index is a specialization of it. So using the n-gram statistics, you can understand that since part of this n-gram is already an entity, you can guess that looking at the probabilities, oh, this should be an entity too. And as a result, then you get basically this ranked list of different n-grams, which should be or should not be treated as entities. So you can have a look at this paper from www for the details. Let me then give you just a bit more detail about the second step of the approach, right? This is a pretty exciting step. So now, basically, we are at the stage where we have understood, or actually the program, the software has understood that the President of the United States is an entity, right? Now the big question is, what should we link this the President of the United States string to? Obviously, it could be linked to Barack Obama, right? But it could be linked to George Bush Sr., all kinds of presidents of the United States, right? Perhaps it can be even hypothetical. And perhaps the article is talking about Trump or Hillary Clinton, right? Which could be the next president of the United States. So it's a very delicate game to link a mention, we call this a mention, to an entity in the knowledge graph. So this is an old problem. You have dozens of good algorithms to solve it. All of them famous to some extent, obviously. This is a very hard problem, right? It's hard, I say on the slide, especially for machines, in the sense that for humans too, it's very hard, right? If you read a technical article and you don't know who is the president of some country, for you it's going to be very difficult to mentally kind of understand that the president of that country is this guy or that guy, right? So it can be very tough for humans too. So how can we solve that problem? Well, we cheated a bit, in the sense that we thought, okay, people have been working on this problem for as long as computer science exists. So let's take a different pick on the problem. What if we want to combine the different approaches, right? Instead of creating a new approach. And also, what if we want to leverage human computation to help us solve that? So you might know human computation or crowdsourcing, right? You have a bunch of platforms like Mechanical Turk, which we use a lot in my group, to basically send some small questions to users online. They will solve those small questions, and they will get back to you the answers, and you will pay them a minimum amount of money, or whatever you might want to pay them, right? But typically it's a few cents to basically solve a small problem. So what we're doing in the end is, trying to combine all the algorithms with a bit of human intelligence to do a better job at guessing who is this president of the United States in the text. So that's the approach we've been devising. It's called ZenCrowd. Also, you can have a look at this paper if you're interested in more detail. It's what we call technically a three-stage blocking approach. A blocking approach is basically an approach to cut some of the search space in that problem, right? Because the search space is ginormous, it's gigantic, in the sense that for each potential entity that you detect, you have basically to potentially check all your entities in the database, and typically you have millions, hundreds of millions, perhaps billions of entities. You have to check all of them and decide, oh, is this related to that or not? So we have different ways to prune that search space. It starts with IR methods like inverted indices. Then we use semantic similarities. And in the end, at this point, we use algorithms to do that for us. And then we kind of decide, should we ask humans to help us or not? So that's a bit the diagram, right? The high-level view on the system. And I think it's pretty cool. So that's why I will spend just a few more minutes on it. So this is the systems and crowds. On the left, you have the input. It's basically text. In that case, we take HTML pages, but we could take TXT, a PDF, tweets, etc. On the right, you have the integrated text, right? So you have the text with some entities which are linked to the entities in our knowledge graph. And we use an open knowledge graph called the LOD, Linked Open Data Cloud, for that, which basically contains billions and billions of entities. Okay, so what happens? You have the text as input. First, you try to extract the entities, as I told you in the first step, right? So you try to understand, is this an entity or not? This is already very challenging, as I told you. Then we try all kinds of algorithms to match this potential entity with the entity in the knowledge graph. And then we have a probabilistic network, right? So we use factor graphs, and we use basically some Bayesian probabilistic network to put probabilities on whether or not this mention corresponds to that entity. And then we have a choice to make. Either we have no clue about this entity, right? Perhaps it's not an entity, perhaps it's not in the knowledge graph. We basically drop the case, because no way we can know what's happening. Perhaps we are very sure that, you know, typically Barack Obama corresponds to this entity whose label is Barack Obama in the knowledge graph, right? So if we are like 95% sure, we'll simply output the link as a result. And in many cases, we are in the gray area. We are a bit in between, right? We have understood that the President of the United States is a correct entity, but we are not sure. Should we link it to George W. Bush or George Bush Sr.? So in that case, we will create an HTML page with a small quiz, send it to a crowdsourcing platform. In our case, it was Mechanical Turk, and we will ask people, right? Okay, here is the part of an article. What do you think? Is it this entity, that entity, that entity, or perhaps it's not an entity, right? And we aggregate the information from those Turkers, from those users of Mechanical Turk. We add this to the probabilistic network. We have a giant kind of learning algorithm on top of it, and then we will decide, okay, it seems that our users are telling us that this is actually George W. Bush, and we will link it to George W. Bush. So an interesting question is, does that work, right? So intuitively, yes, it works, because we are cheating. Remember, we are using humans to help us in this very difficult task. But it's much more actually interesting than that. So we improved precision by 14% on average, which is huge, right? It's a huge step forward in terms of entity linking. And we got to almost, I would say, 80% precision, which, by the way, I think is kind of the maximum in that particular kind of task, because you know, very often it's ill-defined whether you should link those two concepts or not. I can give you a few examples. For example, our method extracted as an entity Italian, right? Italian, the kind of adjective. So should you link this to Italy or not? Some of our users said, of course, Italian, that's Italy, right? But more strictly speaking, obviously, those are different concepts. So it's very difficult to have a 100% in this situation unless you really specify everything using like 10 pages of specification. And in that case, no one will work on the crowdsourcing platform on your task. So 80% is kind of, you know, not perfect, but it's very good, I think, in that context, given that the extraction of the entity is automated. So that's a bit what we got from the users, from the crowdsourcing platform, right? And again, it's very interesting. You have, on the x-axis, you have the number of tasks that the users solved, and on the y-axis, how successful they were in really getting the right answer. And as you can see, so we had US and Indian workers working on US news and Indian news and Swiss news as well. We tried all kinds of different experiments. You can see that some do very well. Like you have a couple of guys here who all the time they clicked on the right answer according to our own judgment. But most of the humans, they are like, below 50%. So my point here is that, those crowdsourcing techniques, they are super cool, but you have a lot of noise in terms of what you get from the humans. But it's still, you can, filter out this noise and get some interesting answer, because a random guess would still be much below, right? We give the humans 4 or 5 different choices, so a random guess would be somewhere here. So you have a lot of noise, but this noise contains tons of interesting information. And by having this probabilistic process, we would still be able to filter out the nice answers and get to up to 80% in terms of precision. Okay, let me go a bit faster over the last 2 stages of this pipeline. So now we have entities. We have entities which are linked to the knowledge graph. Now what we want to do is type this entity. We want actually to guess what is the fine-grained type of that entity in the article it was mentioned. So this is an entity which is obviously defined in our knowledge graph. It's Bill Gates. And in the modern knowledge graphs, actually, entities have tons of specific types, right? So if you look on DBpedia, which is the kind of data equivalent of Wikipedia, Bill Gates will probably have 40 different types. From thing, this is the most generic type, everything is a thing, to person, it's a bit more specialized, to Windows people, to Harvard University dropout, right? Because he dropped out of Harvard at some point. And what we want to do in this third stage is pick the most important types given the context of the article. Why do we want to do that? Because if we understand that, we understand kind of half of the article, right? If the article is about Bill Gates giving a talk at Harvard University, probably you don't care that much that he's a philanthropist, right? You want to say that, he was at Harvard University before. So that's our solution, it's called T-Rank. What is exciting about T-Rank is that it goes much, much beyond the traditional typing that we do. So traditionally, information retrieval, you had kind of 5 or 6 types for your data, right? You would say, oh, this is a person, or this is a location, or this is a company, this is an event. So in our approach, we have 500,000 types, right? So we can get in much more detail in terms of what kind of types interact with each other in the documents. So we have this gigantic tree hierarchy of the types, 500,000 types, the depth of 19 of this tree, so we have types and subtypes and subtypes. And then we have this automated pipeline which uses big data and machine learning to be able to understand that in this article, actually Bill Gates is mostly referring to, the Harvard dropout. It's most relevant for this text. Once we do this, we can also do the very final step of our pipeline, which is called co-reference resolution. So that's also a very interesting and very tough game. It's basically, trying to interlink the different references of the same entity in the text, like the he, she, the president, Barack, the head of state, right? All those labels could reference Barack Obama. And so far, people have been solving this problem in terms of syntax, right? You have some rules, and you try to understand, okay, he, so it must be a male, so I can look at it syntactically, and this should be that or that element. But in many cases, obviously, you cannot solve those co-references if you don't have a bit of semantics, if you don't know something about the entities. Here is a very simple example. Barack Obama called Angela Merkel last week. The president asked the chancellor, right? Syntactically, you have no clue if the president is Angela or is Barack, right? For you, as humans, it's obvious, right? Because you know that Barack is the president and Angela is a chancellor. Well, we can do exactly the same process if we apply the first 3 steps of our pipeline, right? If we know that Barack Obama links to an entity, Barack Obama, in the knowledge graph, and if we know that one of the prominent types of Barack Obama is president, then this game is almost solved by itself, right? Because, it's obvious, Barack Obama refers to the president, and the chancellor corresponds to Angela, right? So that's what we did recently. We extended the Stanford coreference pipeline to incorporate semantics and to be able to analyze this automatically. Why? Obviously to get even more information out of the text. So that's all I wanted to say in terms of the techniques. I will just now spend 5 minutes on applications just to let you know a bit how you could use this in practice. So I will talk about enterprise search, paper recommendation, and what we did recently with Microsoft, which is using this to solve problems for Hadoop. So let's delve into it. The first obvious application of all of this is enterprise search. I told you at the beginning, right? This is a huge problem for any big company today. You have all those pieces of data which are sitting somewhere on a data lake, right? In an HDFS cluster or something. And no one knows what's inside, first of all, this HDFS data lake, and no one can really integrate all those pieces of data automatically, right? To integrate ERP data from a customer with emails corresponding to the same customer, with perhaps internal web pages about the customer, and perhaps tweets about the customer who might have done something recently, right, in the news. So basically, that was the vision, and that's how we implemented it using the techniques I've been telling you about. So I will not get in too much of the details, but basically what we did is we took the knowledge graph and then we kind of developed a way to query this knowledge graph using keywords. And this was published at CIR a few years ago. CIR is one of the top IR conferences, so it was kind of very funny to see that even a few years ago, they realized that bridging keywords with something very different, which is the semi-structured graph database, was interesting. It was kind of a new problem, how to query this graph database using keywords. The second example is actually a live example. You can go to that website, sciencewise.info, and look into this. It might not sound obvious because actually the public is physicists for this application, but we had a lot of fun building that. What's the issue with physicists and papers published in physics? It's like in any specific domain, you have tons of publication, right? In my domain, it's the same. If I want to follow all the publications talking about entities and entity linking, it's very tough. Why? Because obviously you have different communities publishing papers on those topics. And entity linking is called 5 different ways depending on the community you are belonging to. So if you do just simple keyword search on Google Scholar or on any kind of portal, you will not get all the papers that are relevant to your field. So that's what we tackled with ScienceWise. It's a portal which is based on a knowledge graph. We have a deal with Archive. Archive is this open source archive of physics papers. Most of the physics papers, they are on Archive. We parse automatically all the papers. We extract concepts, entities from those papers, and then we link them to this knowledge graph, such that you can be a physicist, you can register that you're interested in neutrinos or any kind of black hole phenomenon, and automatically the system will check all the papers and recommend you new papers to read, even if they don't have the word neutrino or black hole in them, but they are definitely related in terms of the content. And obviously this could generalize to all kinds of other fields, to all kinds of text, basically. And the third one is pretty exciting. It's what we did very recently with Microsoft. So you might know that Microsoft is doing pretty well in terms of the cloud, right? They are one of the biggest cloud providers in the world. Actually, I guess they are second today. And they are growing fast. The other interesting point with Microsoft is that they have the biggest Hadoop clusters in production. So I'm not sure I'm allowed to give you the numbers of machines in each of those clusters, but they have tens of thousands of machines in each cluster with a Hadoop installation on top. Right? And they also have Cosmos, which is their own version of Hadoop. So basically, the issue is that they have tens and tens of thousands of machines in one cluster running Hadoop, and they have petabytes of logs from all those machines, right? Hadoop's logs, HDFS logs, Spark's logs, Cosmos logs, higher level application logs. So every day they have petabytes of logs in tens of thousands of machines. And it's impossible for them to understand what's happening in those clusters, right? And it's a generic problem with Hadoop at this point. So it's very difficult to understand what's really going on and how to debug all of this. And we're talking about millions of dollars for them, right? Those are extremely, tens of millions of dollars. This is very expensive. So what do? Before we build the system for them, basically, an engineer having some issue with some click logs pipeline would manually go over like dozens of logs from dozens of systems, would launch then a pipeline he programmed manually to understand what's going on between those different logs, wait 10 minutes or 10 days, depending on the query, because again, we have petabytes of log daily, and finally get some weird result you would have to inspect manually. What we build is basically an entity engine, a knowledge graph, to solve all of this in a much simpler way. So we take the petabytes of daily logs, which are here, we parse them using those entity extraction, entity linking, entity typing techniques, and we build a knowledge graph out of all of this. We call this a dependency graph, actually, which gives you the dependencies between the jobs, the machines, the files, the users, right? It links all of this in a graph. And then this graph is a few gigabytes or terabytes big, right? So it's still big, but much smaller than that one. The big advantage is that then you can have declarative processes on top, and the user simply has to write a small query to understand the relationship between his jobs and other jobs, files, machines, customers, etc. So that's the architecture. I will, I guess, skip it. And this is used in production already by Microsoft, so they've been using this for auditing and compliance, right? Increasingly, you have those very strict laws which tell you that you should know what's happening with your data. So they've been implementing this using this new system. It was not possible before. They're also using this for job scheduling, right? To understand which jobs are important and which jobs are longer than others, to rank the job, and interestingly also enough, to migrate customers across data center, which is a very tough problem. So Theo is telling me that I should urgently stop, so I will stop here. Thanks a lot. If you have any interest in terms of those techniques, please have a look at our website, exascale.info. By the way, we are hiring PhD students and postdocs, so talk to me or send me an email if you're interested. And finally, I would just like to thank our sponsors. Without them, all of this would be, of course, impossible. Thanks a lot for your attention.